Bismillah ar-Rahman ar-Rahim. Okay, it's because the recording I did on Thursday was not good, so I'm doing this using PowerPoint. This is lecture 3, and I'm reviewing the electric field due to uniform charge distribution or continuous charge distribution, as I mentioned in class several times. So, as I think I mentioned several times, this is a very, very easy topic, but there are a lot of calculus, so you have to be a little bit careful with your calculus and especially integration. So what's meant by continuous charge distribution is nothing more than if you have a charge, oops, so if you have a charge, that is distributed over the volume, over this volume, and you want to find the electric field at some point here, and if this charge is positive, then the electric field in this case is away from the charge. And the way you do that is by taking a delta Q. This is, in this case, this is the volume, so you take a delta Q, which is equal to rho V from these definitions, and you simply take that will give you an infinitesimal contribution of the electric field, and that is due to this charge dq. Now, sorry, again, I just have to make sure that this is the way. So again, so in order to do that, in order to do that, you need, in order to calculate the electric field, all you have to do is just integrate over the volume in this case, and you get E because it's uniform, so you get E, and that will be simply the integration of this. K delta Q R is the distance from the volume in this case, and R hat just gives you the direction. And we have only 3 cases to consider. In the case of a volume, dq is equal to rho dv, and in case of an area, volume, that will be a sphere, and in case of an area, that will be something like the sheet that has a charge distributed uniformly over it. dq will be sigma dA, and in the case of a line charge, dq is lambda dl. And I think I mentioned that, or at least we explained that in the class very well. So this is sort of a summary of all that, and the volume charge distribution, the surface charge distribution, and the linear charge density or charge distribution. Volume is a sphere, surface is a sheet, and linear is line. Okay, so let's take the first example where I have a charge that is distributed over a ring, and I wanted to find the electric field at this point right here. So I want to find the electric field at this point right here, which is located a distance x away from the center of the ring. So the way I'm going to do that, I'm going to use the definition that we have established by simply taking a delta Q. In this case, this is my delta Q, and I wanted to calculate the contribution of that delta Q or the electric field due to that the dq at this point. And of course, I'm going to integrate over the full or the whole ring after I finish. So this will give me, as you can see, the delta Q here will give me, of course, this is the electric field that is going to give me. It has 2 components in this case, 2 components, EX and EY. Okay, and the one thing that I mentioned again in class is that over the ring, you notice that, well, this is, there is another dq here that will give me a contribution that is equal, or that will give me something like this. So this is another EX, and the one thing I want you to notice is that one thing that I want you to notice is that the electric field here, this guy, or the electric field along the y direction will cancel because they are equal, and all you have to say is just because of symmetry, Ey will cancel, and the only thing that I'm going to have is Ex. So my electric field again is simply, so the electric field will be Ex, this electric field here will be Ex I hat, Ey j hat, and then the Ey, when you integrate over the whole ring, it will give you 0. And Ex, of course, you have to project it along X, so that will give you the cosine, you have to multiply by cosine theta. All right, so let's do this integral. As you can see here, so all right, before I do that, so Ex, so E is equal to Ex, and it's k dq x squared over r squared, and cosine theta is this guy, that's cosine theta, which is simply x over x squared plus r squared. But one thing you should notice here is that all of these guys are constant. So at this point here, x is constant, does not vary, and r is constant. So in fact, all of these guys go out of the integral with the exception of dq. So I really, what I should have here? I should have all of this here, and then I have to integrate over dq, and dq, as you can see here, dq is equal to lambda ds, and s being the arc. Okay, so the s here will be the arc, r theta, this arc here, right here, r theta, and theta will go from 0 to 2 pi, so that it completes the ring. Okay, so d theta from 0 to 2 pi is simply theta, and as I said, I mean, theta, and you integrate is 2 pi. That's the result of the integration. Okay, so R is my, that's my small, it should be big R, because I call it big R. Okay, and so that's what I get. That's what I get for the electric field. The X component of the electric field is there. All right. So, all right, so this is my result, which we've seen in class. Okay, and it simply is a function of the the two-dimensional parameters x and r. X is the distance away from the center, and r is the radius of the ring. Now, what I wanted to look at, and this will always be the case, is to look at the limits. What happens if x, if this point is located here somewhere at the center, or if this point is located very, very, very far away? Well, if it is at the center, then E is simply equal to 0, because remember, and I forgot to mention that here, this guy here is nothing more than Q. So this guy here is lambda 2 pi r times lambda is Q, because if you remember, Q is equal to lambda multiplied by L. And in this case, L is simply the circumference, which is 2 pi r. So this is my Q, and that's the result I get. So if x is equal to 0, as you can see, you have x here. You have well, 0 over 0 is equal to 0. Okay? So at x is equal to 0, that is equal to 0, which is okay, because in here, if you look here, there will be a contribution this way, and this guy, this delta Q here will have a contribution this way, and these guys will cancel. All right, I get x is equal to 0. Okay, what happens if you have very, very, very far away somewhere here? Well, in order to understand that, we need to go back to this equation and rewrite it by simply taking x, a common factor of these guys, x squared. So if I take x squared here, and so so that means this will be 1, and this will be a squared over x squared, and I have x squared. X squared to the half, the square root is x, and because I have the cube here, I get x cubed, and that's where I get the x cubed from. Okay, and I have an x from the top, so eventually this guy will go with one of these, and I have q over x squared multiplied by this. Now, if x is much, much bigger than a, so this will be 1 over infinity. That will give me 0, and then I have 1 over x squared, and that's the sort of the result that I expect if you have, it's basically the electric field due to a point charge. So what you're saying, we're saying that you're somewhere here, very far away, and you're seeing this ring as a point charge, which is equal to Q. All right, that's it. Second example. So the second example that I have, or we have, is The second example I have is we want to calculate the electric field. Okay, the electric field, sorry, the electric field due to some line charge which goes from 0 to L. So that's the length of the line. And the line charge has a lambda. Okay, where is lambda here? A lambda, which is coulomb per meter. So linear charge density, and we want to find the electric field here. Again, with the same argument, dq will give me a dE, which is directed this way because you're placing a positive charge right here, a positive test charge right here. And this will have an x component and a y component. And symmetry will tell me that there is another one here, exactly the same way, that will give me another x here, dE this way, and it will have an x component and a y component, and the y components will cancel again. So I'm going to get the same, at least the first lines. I'm going to start, I'm going to start with this. E is equal to Ex plus Ey, and the Ey will be 0, so because of symmetry. And then I have very similar to what I had before, where dq over x squared, this is r squared, and which is the square root of x squared plus y squared, and then cosine theta. In this case, this is really theta, not alpha. So cosine theta, which is equal to x divided by x squared plus y squared. So if I do that, then I have to solve this this integral, which is again I wanted to put everything in here. So you see that all I've done is dq, and I put this is cosine theta, okay, and as you can see, it's x over that, and dq is lambda dy. So dq is equal to lambda dy, and dy goes from y goes from 0 to L. So I have to integrate this integral here, where x is fixed, right, and y is the variable that goes from 0 to L. If I integrate that, I'm going to use something from the table standard. Okay, from standard tables. So this is from my standard integrals. So something like that will have 1 over a squared. My a is x. Remember, a in this case is x, and x is y. Okay, so that will give me, if I do that, that will give me this. So 1 over x squared, right? And then y is my variable, x squared plus y squared, or a squared plus y squared. Okay, and then it's from 0 to L. So if I do that, then I have so you have to do that. You have, yeah, when this is L, so this will be L squared plus x squared, and when it's 0, it will be 1 over x squared. And I think I have it in the next yeah, L squared, and that's, sorry, what is this here? Okay, so when L is equal to 0, this will be 1 over x squared. Okay. Oh, sorry, when x, because you have an x, yeah, you have an x here, x squared, 1 over x is equal to L over there. Okay. So when L, let's examine, try to examine the because it's y. Oh, sorry, and that's why the there is a y here. Y here. When this is 0, so this guy is 0. It's really survives only when y is equal to L. So that's why this survives only when y is equal to L. So the result that I have is this, right? And I wanted to examine both cases. When x is equal to 0, if x is equal to 0, that means I'm right here. Okay, and as 1 over 0 is infinity, that means the electric field is infinity, and that's expected. Okay, because you're right at the surface. Right? And if you remember, I think I explained that in class. You can also explain this using the argument that the relationship between E and R is that when R, so this is R, when r is equal close to 0, e goes to infinity, and that's exactly what we have. So when r, this is in case that's r equal to 0 right here, then e goes to infinity. So that's consistent with that. Now, what happens when you're very, very, very far away from, so you expect to see something that, electric field due to a point charge. Okay, so the way to do that is by simply taking again x square as a factor, and then you take that. So x and x square, you get another x here, so that you get xx, which is x square. And this will be over x square, that will be 1, and this will be over x square, something like that. And when x is much, much bigger than a, in this case a is L. Okay, so when that's the case, then this becomes 1 over something that is very big, which is 1 over infinity is equal to 0, and then you get q over x squared, and that's the result you expect. All right? Okay, so that's the electric field due to the electric field due to a finite line. Now, which is, as I said, the electric field due to a point charge. Now, what happens if the line is infinite? If the line is infinite, so it goes from minus infinity somewhere here to infinity there, then the limits will be as follows. So the electric field will be twice 1 over x, and forget the k here, lambda, forget the k lambda here, but the limits will be 0 to infinity. So I'll integrate from 0 to infinity, and then I multiply it by 2. If I look at the limits here from 0 to infinity, when y is infinity, 1 over infinity is equal to 0. 1 over infinity is equal to 0. So I have 2k lambda over x, which I have it right here. When y is equal to 0, so 1 over 0 is 1 over infinity. 1 over infinity is 0, and 1 over 0 is 1 over 0 is infinity, right? When when y is equal to 0, I get 1 over infinity, which is equal to 0. Okay, so that's done. So the electric field due to an infinite line that's carrying a uniform charge distribution density lambda is defined by this, defined by 2k 1 over 4 pi epsilon, of course, and lambda divided by x. So this is only for you have an infinite. If it is finite, then we get this equation right here, or these two expressions, this expression here, and I get the two limits from it there. Okay, or you can definitely, if you write this 1 over 4 pi epsilon, then 2 will cancel with the 4, and you get 1 over 2 pi epsilon naught and lambda divided by x along the I hat. Okay, the third and last example, we want to find the electric field due to a sheet uniform charge distribution over a sheet, which is area, and at a point here somewhere. So dq, this dq here, is nothing more than sigma dA, and A is the area, which is pi r squared. So dA will be simply 2 pi r dr, and you have the limits from 0 r, the limits of r from 0 to r, from here all the way to here. Yeah. And again, I wanted to do the same thing. That's my definition for the electric field due to a uniform charge distribution. And again, the y will cancel, or the y contribution of the electric field will cancel because of symmetry, and I only have the x contribution. So that will again give me the same exact as I had before, except now it's a little bit different. So if I combine these two together, then I get that. Okay, so dq is sigma. Let me write that down. Where's the pen here? Okay, so dq is equal to sigma dA, and A is pi r squared, so dq will be equal to sigma 2 pi r dr. So if I take the sigma out, and the 2 pi will cancel with pi, and I have a 2 here, that's my 2 here, and epsilon naught here, so I get sigma x over 2 epsilon r dr, and then over this square, which is simply this distance here. That's what that is, okay, to the power of 3 halves. All right, So how do I integrate this? Well, I integrate this using a trick by simply letting this, defining this as t. So my dt is 2 rdr. I have the rdr. So if I multiply by 2 divided by 2, I get the 2 here, and then I get the 2rdr. All right, and then I place that. So if I do all of that and I integrate from 0 to r, so this is 3 to the power, I just took this upstairs, so it's minus 3 halves, and minus 3 halves plus 1 is minus 1 half, and divide by minus 1 half, and these guys will cancel. So this is the result I get, minus sigma over 2 epsilon, and then I have 1 over x squared plus r squared from 0 to r, and I get sigma x over 2 epsilon naught. And when small r is equal to big R, I get that. And when minus that will give me plus. When r is equal to 0, I get that. All right. So this is the result I get for the sheet. The electric field is sigma multiplied by that. And now I wanted to check the limits. In order to check the limits, I need to rewrite this way. All I've done here, I just took this x here, okay? This x here, and just multiply it here. So if I multiply that here, I have x, and then I have 1 over x, so that will be 1. So x divided by x is 1. Now remember, I have x here, and if I take the x squared out, so that will give me x here, and that x will cancel with this x here, and then I have this expression here. Now I want to look at the limits. What happens when r is much bigger than, when r, this is my radius, is much bigger than x? That means I'm at a point where I'm very close to the surfaces. So that my x is very small in comparison to r. That means I'm very close to the surface of the sheet. If that happens, so I know that 1 over something that is very big, so 1 over something that's very big, that gives me 1 over infinity, which is equal to 0. So this term goes, and then I have the electric field equals to sigma, so the electric field is equal to sigma over 2 epsilon. All right, and that's the result that somehow we've seen it before. Again, taking sigma as epsilon times a, then I get the result, the electric field is equal to q divided by 2 epsilon multiplied by a. Okay, now let's use this result that we got to calculate, this is a question in the homework, to calculate the electric field at this point here, and this point here, and at this point here. Now if you look at the electric field due to the negative charge, it's away from the line charge, or from the sheet in this case, and its magnitude is sigma over 2 epsilon, and this way it's sigma divided by 2 epsilon. And for the that's for the positive charge. The positive charge is away. For the negative charge is into, and it has the same magnitude. Now if I put these guys together, then in region 2, this is region 2. In region 2 I have this sigma here plus 2 epsilon plus so if you're in between them in here, the electric field due to this guy will be this way, and the electric field due to this guy to be this way. So you add these two. So these two are added, and then you get the electric field in region 2 is sigma over 2 over epsilon. Half plus half is 1. And in region 3 and region 1, you subtract, because in region 3 and region 1, the electric field due to the positive charge is this way, and the electric field due to the negative charge is this way. So they subtract, and therefore the electric field in this region is equal to 0, the electric field in this region is equal to 0, and the electric field in this region is equal to sigma divided by S. So that's all, and I'll see you next class, inshallah. Thank you very much.